Welcome to Unit 6 of Chemistry 101 at Goodwin College. This this week, we are going to cover chemical reactions and chemical equations. This is basically equal to the second half of Chapter 5 in your textbook. So before we begin that, I think it's probably worthwhile to sort of have a brief review about what we did in the previous unit, so let's do that. One of the first things that I want you to be able to do is be able to read the periodic table. For most of you, this shouldn't be a problem. If it is a little bit of a problem, just sort of take this as a refresher. Each element in the periodic table is sort of usually enclosed in a box. There will always be a whole number, which is basically telling you the atomic number, which is how many protons that particular element has. There's an abbreviation for the element, also known as its symbol, and then there is another number that is usually not a whole number, although sometimes it can be for some of the stranger elements. This other number is known as the average atomic mass. In other words, that's basically how much one atom weighs of that particular element on average. The other thing, it also means something else that we covered in the previous unit, and I'll get to that in a minute, but you can think of this as telling you that the average hydrogen atom has a mass of 1.0079 Daltons, or 1.0079 atomic mass units. And you can do this for any of the elements, so you should be able to read this type of information for oxygen, for fluorine, for neon, whatever shows up on the periodic table. So that's the first part of the review. Second part of the review is that you can sort of compare the masses of different atoms. So you can basically look and say the average atomic mass of hydrogen is a little bit over 1 Dalton. The average atomic mass of beryllium is a little bit over 9 Daltons. And what that means is your average beryllium atom is about 9 times heavier than your average hydrogen atom. And so you should be able to do that for any two atoms. As an example here, nitrogen, your average nitrogen atom is about twice as heavy as your average lithium atom. And again, I'm rounding to the nearest whole number. So your average lithium atom has a mass of about 7 Daltons. Average nitrogen atom mass of about 14 Daltons. So nitrogen's about twice as heavy as lithium. Okay. The other part of the review, again, we talked about this last week. Molecule, our definition of molecule is 2 or more atoms that are attached to each other. If I just write the capital letter H, that means 1 hydrogen atom. That's not a molecule. However, if I write the capital letter H with a subscript of 2 to the right, that means 2 hydrogen atoms attached to each other, which makes 1 hydrogen molecule. So I can write H2 in a slightly different way. I can write it H with a solid line between, in the middle of 2 capital H's. This basically means 2 hydrogen atoms attached to each other. And this whole thing here is 1 hydrogen molecule. And again, I won't spend too much time on this, but basically if I write capital letter H with a space, another capital letter H, then capital letter O, I am telling you that we are talking about atoms, 2 hydrogen atoms, 1 oxygen atom. But if I bunch them all together, then this is called a chemical formula for water, and this is 1 water molecule. And because they're bunched together, you're basically implying that those atoms are not free to move about amongst themselves however they want. These atoms are actually attached to each other in some way. Okay, and then we talked about molecular formulas, and hopefully you should be able to read them with a certain amount of confidence. You should be able to look at this formula, which is admittedly a little bit of a mouthful, but if I asked you how many carbons, you could scan along and you could say, look, there's 1, 2, 3 carbons. There are 2 oxygens. There are 3, 4 hydrogens. There's 1 nitrogen. And, oh, I think I missed a couple hydrogens. So there are 3, 4, 5, 6, 7 hydrogens and 1 nitrogen. So you can see that it's a little bit easy to mess that up, especially when I forgot to color code the hydrogens over here. But you should be able to scan along and count the number of each type of atom. So this one is a little bit simpler. This thing has 6 carbons, 12 hydrogens, and 6 oxygens. This molecule down here is nitrogen gas. It is made of 2 nitrogen atoms attached to each other. And then this was a little bit of the more difficult one. when you have parentheses and then a subscript to the right of the parentheses. This subscript to the right is telling you how many groups of whatever it is inside of the parentheses that you have. So for this particular molecule, the formula is telling you that you have 1 calcium, you have 2 sets of NO3s, which means you have 2 nitrogens and 6 oxygens. We did water. If you put the number 2 in front of the H2O, and I asked you previously what this means, and usually students like to think of this as meaning 2 water molecules. And this over here, because there's no number written in front of the H2O, the number 1 is implied. So the beginning students tend to think of this as meaning 1 water molecule and this meaning 2 water molecules. What it really means, and you'll see this in this unit, is that the 2 here really means twice as much as whatever I'm referring to over here. So this could mean 2 water molecules, and then this would mean 1 water molecule, but it could mean 2 dozen water molecules, and then this would mean 1 dozen water molecules. The reality is that what this number means depends on the situation, and it depends on the type of question that's being asked. So it could mean 2 dozen, 2 billion, 2 trillion, it could mean 2 moles compared to 1 mole. And you'll see that that's the more common, as we go through this unit, you'll see that that's the more common way of thinking about it. Thinking about this number in terms of how many moles of something you have, and then this, if there's no number, meaning that you have 1 mole of something. And then if you did that, then you could potentially have 3.58 moles of water molecules. Okay, and so now that we're talking about moles, just a refresher, you can think of the mole in chemistry as being roughly equal to the same type of concept as a dozen. So a dozen is 12 of something, so if you have 2 dozen, that means you have 2 groups of 12. 1 mole is 6.02 times 10 to the 23 of something. So it's just grouping things in groups of 6.02 times 10 to the 23 in the same way that a dozen is grouping things in groups of 12. Let's see. The other thing that I mentioned at the very beginning of this portion of the video was that a lot of times you can think of this as how much the average mass of a hydrogen atom is, this number over here. So hydrogen's average mass is a little bit over 1 Dalton. However, this number is also used to tell you the mass of 1 mole of hydrogen atoms. So if you have 1 mole of hydrogen atoms, which is 6.02 times 10 to the 23 of them, the mass of all of them together is about 1.0079 grams. Now the units have changed from Daltons or atomic mass units, they've changed to grams. So if you have a pile of hydrogen atoms and you have this many of them in your pile weighs a little bit over 1 gram. And then you can do that for any of the elements in the periodic table. You can basically say, look, your average helium is about 4 times heavier than your average hydrogen atom. If I have a pile of hydrogen atoms and the pile has this many hydrogens in it, it weighs about 1 gram. If I have a pile of heliums and I have the same number of helium atoms, since they weigh 4 times as much, my pile of helium atoms is now going to weigh about 4 grams. So that's the mole. I'm going to summarize it again on this slide. Mole is just an easier way of saying this number, in the same way that a dozen is just a different way of saying the number 12. 1 mole of an atom equals the average atomic mass number of that atom in grams. So if you have a mole of heliums, they weigh about 4 grams. And then sometimes this number is referred to as Avogadro's number or Avogadro's constant. And this, I'm showing you again this slide because I will repeat these phrases over and over again, probably for the rest of the course. If you know the number of moles of something, of some chemical, and you know its chemical formula, you can figure out how many grams of it you have by looking at the periodic table. And you can do this in reverse. If you know how many grams of some chemical that you have, and you know its chemical formula, you can figure out how many moles there are of this substance. So just as an example, chlorine, if I told you that you had 2 moles of chlorine, you could look at this piece of information and you could say, look, the mass of 1 mole of chlorine atoms is 35 roughly 35.5 grams. So if I have 2 moles of chlorine, it must weigh about 71 grams, which is 35.5 times 2. And then you can do this in reverse. If I told you that you had 35.5 grams of chlorine, how many moles do you have? You can basically look at the periodic table and say, oh, I have 1 mole, because that information is being told to you by this number. Molar mass, we just basically talked about it on the previous slide, but more formally, molar mass is the mass, or if you want, the weight of 1 mole of some molecule. It's basically answering the question, how many grams are there if I had a mole of some particular substance, or a mole of anything? So the molar mass of hydrogen is 1.0079 grams for every 1 mole of hydrogen. Molar mass of hydrogen molecule, so H2 in this case, is twice as much. You take this number and multiply it by 2, because now we have 1 mole of H2s, and there are 2 hydrogen atoms for every 1 H2 molecule. The molar mass of water is about 18 grams, and the reason for that, the way that you figure that out, is you find the molar mass of each element that makes up water. The molar mass of hydrogen is 1 gram. The molar mass of oxygen is about 16 grams. You actually have 2 moles of hydrogen here, which means that 2 moles of hydrogen weighs about 2 grams, 1 mole of oxygen weighs about 16 grams. If you add up all of the pieces, it comes out to a little bit more than 18 grams per mole. So if you had 6.02 times 10 to the 23 water molecules, they would weigh, altogether, they would weigh about 18 grams. That's what molar mass is telling you. If it's a little bit confusing, and I know that students sometimes are confused by the difference between a mole and molar mass. So what's the difference between a mole and molar mass? Another way of thinking about it is, imagine that I have a pile of atoms here. And let's pretend, although this is not 6.02 times 10 to the 23 atoms, let's pretend that it is. The difference between mole and molar mass is, moles basically say, how many groups of 6.02 times 10 to the 23 do we have? Do we have 1 group? Do we have half of a group? Do we have 3 groups of this? That's what moles mean. Molar mass means what is the weight, or what is the mass of 1 group of 6.02 times 10 to the 23 of something. So the other way of thinking about it is, how much does 1 mole of something weigh? So if this was 6.02 times 10 to the 23 atoms, it would be 1 mole of atoms. And then, since I'm not telling you what type of atom it is, you don't know what the molar mass. The molar mass would basically be not how many of these there are, but how much does the whole pile weigh. So that's it for the review. The rest of the unit will be devoted to the second half of Chapter 5 in your textbook.